How do Newton's three laws of motion hold up to Distinti's rules of scientific acquisition? These are Newton's three laws of motion. We're taking them from Wikipedia. We're going to go over them one by one. I'm just putting this here so you know where I got them. This is Distinti's rules of scientific acquisition. There's approximately 40 rules. Some of them are tells, some of them are imperatives, etc., etc., and we're going to show those that apply to Newton's laws of motion. For the full rule set, you can go to the website and it'll give you the complete list. If you want to see how to get to that, that'll all be at the end of this video. So let's look at the first law. A body remains at rest or in motion at a constant speed in a straight line unless it's acted upon by a force. Now there's other variants of this where they say by an external force, but it doesn't really matter here. I'm going to show you that this first law violates the paradox tell because there's an implied paradox, and it also violates the perpetuity perfection tell. Let's do the paradox tell first. So if I put a brass cannonball and I put that on a drone and I bring that up to a high altitude and I release that cannonball, it's going to accelerate toward the earth. There are people out there that say gravity is not a force, and therefore the cannonball should not accelerate because according to Newton's first law, you need a force to cause acceleration. Okay, but I'm going to let everybody else worry about that because we got bigger fish to fry here. The other issue is if I put a cannonball in space, and assuming that there's nothing else in space here, I just have a picture here to show that this is space, assuming this exists in a space-time that is completely flat, and then I push it at velocity, so now it's attained a constant velocity. Well, according to what physicists believe, this cannonball is going to travel forever and ever and ever and ever. And that, my friends, is a violation of the perpetuity tell. There can be no perpetual motion. Because it's ironic that physicists will slam somebody for saying they invented a perpetual motion machine, but their own law, a first law of physics, is perpetual motion. Now, in ethereal mechanics, there is a medium out there, and that medium has a very tiny viscosity. So over, I don't know if it's hundreds of thousands or millions of years, that cannonball will eventually come to rest with regard to the medium. And the beauty of this viscosity is it solves a lot of problems in cosmology that we're going to discuss when I release the cosmology series. That will be for Patreon members only. And the interesting thing about ethereal mechanics is all bodies that are in orbit around a central mass will eventually attain a perfectly circular, well, not perfectly, a substantially circular orbit. So in time, here's a prediction that ethereal mechanics makes, and you'll see more about it if you apply to sign up to become a Patreon member and see the cosmology series, is that this viscosity in space will eventually cause elliptical orbits like Mercury and Pluto to decay to a substantially circular orbit. And the reason why these bodies are in elliptical orbits is because they were struck or their orbits were affected by a near passerby, what have you. How we explain this, we could explain this same phenomenon with relativity, kinda. That if we take the model that's out there, this fabric of space-time, well, if you have an object that's moving through the fabric of space-time, you are working it. If you are working a medium, that requires a loss of energy somewhere. And where does the energy come from? It's kinetic energy, it's motion perhaps. The problem with relativity is they don't have a reason why an orbit would be stable. With this model for relativity, orbits would eventually decay and fall into the sun. So that's the big difference between what ethereal mechanics predicts and what relativity predicts. Relativity predicts that all orbits will decay and fall into the central mass because they would eventually lose all of their energy by working the medium. So the first law of motion is not a law. It is a useful engineering approximation for applications where the kinetic energy losses are insignificant to the problem at hand. In other words, you're considering systems over a very short period of time, etc., etc., because there cannot be perpetual motion. But you can use an approximation to perpetual motion for small engineering applications. We do that a lot in engineering because nothing is perfect. The second law. Well, I'm not going to read this to you because it is basically a very, very, very fancy way of saying F equals ma. And this has a problem with the intrinsity tell because mass is an intrinsic property of matter that can't be explained. Well, it can be explained by ethereal and you can go back and look through the electrogravity series about that and explains how mass, which is really inertia, is a function of the model of matter. That's a minor issue right now. The other problem that we have here is that F equals ma is not really force, because this is saying that we're measuring force by the object that's accelerating. So this is something that's already occurred because of an applied force. So we're using the outcome of the exchange of applying force to be the representation of force. And if you think I'm making this up, it's right here. The net force on a body is equal to, it isn't, in other words, it doesn't say it is this. It says it's equal to the body's acceleration multiplied by its mass. Okay, so this is not really force. This is a representation of force. And let me put a finer point on this for you. See, I have this guy here. He's pushing on the wall. He's applying force to this wall. But you can't measure. The ball isn't accelerating. So how do you know he's applying force? And a logical person would say, well, all the forces in here are in balance. That's why the wall isn't going to move. Okay, remember that. That's very important for the next slide, but that if all the sum of the forces equals 0, that nothing will move. I'm going to say that again. If the sum of the forces equals 0, nothing will move. And I'm going to say it one more time because I know somebody didn't hear it the first 3 times I said it. If the sum of the forces equals 0, nothing will move. Okay, now let's go to the next step. Let's put scale under his hand, a spring scale. And when he applies force to that spring scale, which is force being applied to the wall, that spring scale will show a force. But nothing is accelerating. How are we measuring force when nothing is accelerating? And somebody's going to say, well, we know the spring equation here, that the force on a spring is equal to the spring constant times the displacement of the spring, which we're going to represent by x. And they're like, aha, Bob, we got you. There is a representation of force that does not require acceleration. Well, hold on a minute. Let's look at the units of the spring constant here. All the spring constant does is take the displacement of the spring in x and divide that out and replace it with ma. So we're still representing force as something that's accelerating, even though our measurement does not have anything accelerating. So this ma is not real. It's a representation of what could happen if the wall were, let's say, on a frictionless bearing and you could actually move it. So what we have here as a representation of force for the past, I don't know how many hundreds of years, is a doppelganger. It looks like force, it smells like force, it allows us to do math and equations as if it were force, but it's not force. It's a representation of force. And the reason why this rule of acquisition has 2 is because this is kind of the short name, but this is actually what's going on. We have mass times acceleration, which correlates to force, but because we're using it, it's obscuring the true nature of force. Okay, this doesn't mean what we're doing is wrong. It just means we don't have the final word. We're using an imposter for doing science and physics and engineering right now. And that is something we have addressed in ethereal mechanics. We're not at the end of down this rabbit hole yet, but we've gotten a couple steps down farther. Now let's discuss Newton's third law of motion. If two bodies exert forces on each other, it's almost like sentiency. They have a choice to do this. These forces have the same magnitude but opposite directions. The way this is spoken other places is, for every action, there's an equal and opposite reaction. Okay, and so if you have an equal and opposite reaction to what your action is, shouldn't the forces cancel? I mean, let's look at this example of the finger pushing the ball. So the applied force would be F equals ma. But because this is an inertia, the inertia reacting to the applied force is F equals minus ma. You look at the sum of the forces here, the sum of the forces is 0 because it's equal and opposite. It's an equal and opposite reaction. So how does the ball even move? How does anything in the universe move, for that matter? So one way to solve this issue is to say, well, okay, when I apply the force, the reaction to my applied force is perhaps delayed just a little bit. That no exchange of energy is perfectly instantaneous. That solves a lot of problems. And in fact, in ethereal mechanics, the inertial force is delayed, and that's explained in ethereal mechanics. I'm not going to explain it here. And that solves a lot of problems. But the other issue here is that it almost looks like they're implying that these guys know that, oh, well, if my force is applied here, then, well, the reaction has to be equal and opposite. How does it know to do that? How does it know to do that? Is there some kind of sentiency going on? No, it can't be. So let me show you that the little bit of lag in the force is the reason that solves all this problem. Let's take a look, and I'm making it on a very large scale, but let me tell you right now, this applies down to the subatomic level as well, because everything, all bits of matter, affect each other through fields. Matter does never actually touch each other. And so all exchanges are done by fields. There's no actual touching of matter. I'll say that again and again. So let's look at it at the very, very, very large scale here. Here we have a star that's on the outside of a galaxy. The star emits a gravitational field, but since gravity doesn't travel instantaneously, it takes, let's say, 20,000 years for the gravitational information of the star being in this position to travel to the center of the galaxy to affect the core, let's say. Okay, in that 20,000 years, the star is going to move to a different location. So when that effect finally hits the core is tugged a little bit in this direction because that's how the force was emitted from that star. But because the core is emitting force out in all directions simultaneously, that when the star does move here, it's going to hit the wave fronts of force from this core as it gets there. So it's going to be tugged toward the core. Now, here's where I'm really going to add a twist in your brain here, because this galaxy is actually moving with respect to the universe. So this isn't going to be exactly pointing at the core. It's going to be pointing at where the core was 20,000 years ago. This lag solves all the problem with regard to dark matter. And we'll explain that in the cosmology series. Again, if you want to see how to become a Patreon member so you can watch the cosmology series, that will be in the links at the end. So Newton's third law, it's not really a law, it's really just an approximation, but it would only be true if field propagation is infinitesimally fast. In other words, propagation time is 0. And since this is never true, then Newton's third law is never true. I mean, it's useful for engineering purposes because in a lot of engineering applications, we can say that the propagation time is small enough that we don't care about the slight error in the vectors. Okay, but again, this is not a law of nature. So in conclusion, Newton's laws are exposed as two engineering approximations and a doppelganger, which is basically an abstraction placeholder for a real thing. They are not laws of nature. If you really want to support this work, become a Patreon member. If you become a passenger above, you will see the cosmology series. It'll only be presented to passenger level patrons and above. I'm not going to make it public. This is the repository. When things are made public, they're put here. If you want to learn how to navigate through the repository, go to the introduction video on the YouTube site, where you should be able to get to it from ethereummechanics.com, but I'm having problems with the SSL certificate on this, and sometimes it gets rejected. So just go to YouTube and search for Ethereum Mechanics and look for this logo, or you can go at Ethereum Mechanics 5686 blah, 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 blah. This is the blog site. Great shout out to Sebastian for taking care of this. Let my folks know that I'm working on a plan to expand my ability to work on Ethereum Mechanics with more time. I have a plan. Don't know when I'm going to activate it, but I'll tell you more about it on the Patreon side later. Thank you. No more voodoo physics.